Good morning, or good morning, good afternoon, everybody. It's not morning, it's afternoon. Good afternoon. Welcome to another exciting afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. Now, I have to talk about something personal right now, and that is you people have been really nice to me, and I appreciate that. So, in light of that, take next week off. Just take the whole next week off. And in case you forgot or don't know, next week is spring break. So party hard. I still got to teach at the other school. And when you come back, I'll be on spring break for the other one. They're not synchronized like they sometimes are. So remember, next week, we have no class whatsoever. However, technically, I'm not even supposed to do office hours, but since I'm teaching at the other school next week, I'll still have my office hour, but I'll go from 5 to 6 instead of 6:15 unless somebody needs help, and I'll stay late like I would anyways. So don't forget next week, spring break, which means I get to start working on my lawn. Yuck. That's not one of my favorite things in life, but it looks nice when I work on it. All right, let's get back to work. Let's talk about esters. And on Monday, I showed you saponification of an ester. And this is the reaction which I'll teach you later on. Our ancestors, and even today they still do it, used to make soap. You know, the stuff you get your hands clean, And later in the semester, I'll actually teach you about soap, and I'll teach you how does soap or detergent work to get things clean. But you know that's organic chemistry. Speaking of organic chemistry, did any of you happen to pick up a bottle of vinegar and think it contains acetic acid, which is a carboxylic acid? Did you happen to pick up a bottle of nail polish remover and see ethyl acetate, and that's an ester? Did you happen to pick up a bottle of mustard and see it contains vinegar, which contains acetic acid, which contains, guess what? A carboxylic acid. Remember, organic chemistry is all around you, and it won't hurt to think about it when you're not in my class or lecture or anything else I'm doing with you in terms of organic chemistry. If we're out playing tennis, no, you don't. I haven't played tennis in a while. My tennis buddy left the area long ago. I never found another one. But anyways, let's get back to organic chemistry. Now let's practice this reaction. We did it on Wednesday, but let's do another one. And I remembered the plus sign. What two products do you get when you treat that compound with sodium hydroxide and water? Your turn. Have you noticed I got my hair permed? Not really. It's my curls coming out. I have curly hair, which I perpetually try and straighten. And I've learned in life, people who have straight hair always want it curly. I guess the grass is always greener on the other side of the fence. All right, it looks like everybody's done, so I better get to work. And if we look at this right here, what functional group, what's different? Ooh, two oxygens, one double bond to carbon, same carbon has a single bond oxygen. On the single bond oxygen, I have carbons to the carbonyl carbon, which you know is carbon double bond to oxygen. I have carbons, we have an ester. And if you react it with a base, hydroxide base, and water, remember M can be sodium, which in our case it is, lithium, or potassium. You get not the carboxylic acid you would have used to make that ester, you get the carboxylate anion of the carboxylic acid you would have used to make that ester. Let's make this, that looks better. And you get the alcohol you would have used to make that ester. So this is R prime, and therefore I get this carboxylate anion, and you do not have to put charges, I always will, and this alcohol. Remember, the carbon, this oxygen is bonded to an R prime, is the carbon the hydroxyl group will be on, which in this case is the center of 3 carbons, an isopropyl group. And I know there are 4 bonds to carbon, so I can put in my hydrogens. And that's what you get. Now on test 3, like test 2, there'll be a couple synthesis, 3 or 4 problems. So let's do one. No. Let's try that again. That's better. And the question would be, what would be the starting material that I react with lithium hydroxide, LiOH, and water, I think you all know that's H2O, to get those 2 products. And don't forget, if you need any help in any way, I'll have my office hour tonight from 5 to 6:15. And I'll be there to help anybody who needs help. By the way, synthesis is the fun part of organic chemistry, but I'm biased. I'm a synthetic organic chemist. Remember, synthesis means this to make. All right, everybody's done. I better get to work. So how do we do this? How do you figure out what should you start to make something? You look at this and say, that's a hydroxide base, water. M can be sodium, potassium. Once in a while, I make that mistake, put a P down instead of a K, potassium, or lithium. In this case, it's lithium. And what do you start with to make this is a carboxylate anion? This is carbon-carbon. Look for what's different. What's not carbon or hydrogen should get your attention like that. And we have a alcohol hydroxyl group. And what do you start with? An ester. What's our, extra carbon in there. Hold on. That's R. And this is R prime. So that means our ester, R, carbonyl, oxygen. Which carbon of R prime has the hydroxyl group? This one, that will be the carbon attached to the oxygen in the ester. And I know there's 4 bonds to carbon, so I can put in my hydrogens. And that's saponification of an ester. And like I said, we'll come back to this. In the old days, they take animal fat, which is esters, and react it with sodium hydroxide and water in a big pot and boil it and cool it down. You see this white solid in there, which is your soap. Now for a very special reaction. Why is it special? It deals with Grignard reagents. Anytime you see anything with Grignard reagents, Dr. White's going to be very happy. Now, one thing I see a mistake here, so I better correct it. I can't on here. This is from my ChemDraw software, but I'll rewrite this. And that's the reaction of Grignard reagents with esters. And let's go to the whiteboard. Now, as I had it written on that slide, for organic chemists, that's correct. To help students out, we have an ester. Here's what I forgot there. To 2. Normally, organic chemists don't balance things. We're lazy, but for students, I will. And on test, I will. And if you react a Grignard with not 1, but 2, an ester with 2 Grignard reagents. Remember, X here is chlorine, bromine, or iodine. And second step, water and acid. What happens? You make not 1, but 2 very special carbon-carbon single bonds. Here was my carbonyl group, is now this carbon right here. And in organic chemistry, there's only a few handful of reactions, very special, that you can make carbon-carbon single bonds. Now, I'd like to show you how this happens. What I'm going to write now, you don't have to copy, and it will never be on a test. It's called mechanism. Dr. White loves mechanisms. And if we take the first Grignard, it attacks the carbonyl, and you lose this. So you get this. This ketone plus this is called an alkoxide. It's the conjugate base of an alcohol. Now, you learn for test number 2, if now I have my second Grignard reagent, second step acid and water, I'll go and to this carbonyl, I'll add another R triple prime. Now, this is a very strong base, alkoxide. So when in the second step I add acid and water, you protonate this to make the alcohol. And this should be R prime. And that should have, and that's how you do it. However, the key thing is to know, and I'll never ask on a test a mechanism, but I will tell you this, a personal story. When I was in graduate school, and I was so fortunate to be have my PhD advisor and be in his research group, Dr. William Roosh, now a professor emeritus at Michigan State. And one of the things he drilled into my head and everybody else's, that was understand how a reaction you're looking at goes step by step. Know the mechanism, because once you know the mechanism, you can do some serious good and have a lot of fun. And that was a lesson throughout my chemical career. I would take the time to learn mechanisms. Other chemists were too lazy or who knows what. And I could do things they didn't because I knew the mechanism. All right, let's take this for a spin. And I actually used this reaction in my PhD thesis to make some. And I should mention up front, this reaction, I will never on a test or a final ask for you to do a synthesis. I know how to do it, but I don't think that's fair for you to have to do that. All right, let's look at this reaction. Give the organic product or products, and here I would have a plus. If we look at this, we say, what's different? What's not carbon? What's not hydrogen? Ooh, two oxygens to the same carbon. One oxygen has carbons on it, I'll call R prime. The carbonyl carbon has carbons, I'll call that R. Then I have, ooh, two of something. Carbon, magnesium chloride, that's a Grignard. Remember, X can be, in this case, it is chlorine, bromine, or iodine. I do have to admit, most of the time I've done Grignards, it's always been with chloride or chlorine as MgX. Second step, acid and water. Keep your eye on the carbonyl carbon. What's attached to it stays attached to it. You'll have not one, but two carbon-carbon single bonds you'll make from the Grignard. And this opens up to an alcohol, which is this carbon. Then this right here becomes this alcohol. So this is my R group. This is my R prime. And this ethyl is my R triple prime. This case doesn't matter, but remember that the carbon with the Grignard will be the carbon bonded to this carbon with the hydroxyl group. So the first thing we'll make, my R group, my carbonyl carbon which is now this carbon with a hydroxyl group. And what are my R group, R triple prime, ethyl? And there are 4 bonds to carbon, so I can put into hydrogens. What's my R prime, methyl? And look at the beauty of this reaction. It is beautiful. Now, you know, I'm an organic chemist. Taking this simple molecule and this simple molecule, I've now made this very complex molecule, which I can use to do things with. Now, one of the, I don't know if it's a trick, but practice, when you're doing this, you keep R prime very small, so the alcohol you make is either water soluble here, the second one, or you can distill it out very quickly because it has a low boiling point. And that's how you do it. Remember, we made not 1, but two carbon-carbon single bonds. Hold on. 30-second rule. I get to change my mind. And there you go. What would be the two products you would get when you react those two molecules together? And like I said in that first step, organic chemists usually don't put the two there because everybody knows it should be there. We don't balance equations, but for this reaction, for you, I will. Thank you, Dr. White. You're welcome. Am I nice to myself or am I nice to myself? Don't answer that. All right, let's get going. And how do you proceed? Well, you look at the different molecules and say, what functional group do I have? Or you ask the question, what's different? What's not carbon? What's not hydrogen? Also, what's not a carbon-carbon single bond? Well, ooh, two oxygens to the same carbon, double bonded, single bonded, that same carbon. On the oxygen, I have carbons. I'll call that R prime. On the carbonyl carbon here, I call that R, and I have an ester. And if I look up here, ooh, the number 2, and I have carbons here, R, I'll call that triple prime, magnesium iodine. And that's the halogen. And for this reaction, the halogens can be chlorine, bromine, or iodine. Second step, acid water. Remember, H plus is acid, H2O, I think you all know is water. I hope so. And what do you get? You get, first of all, what's attached to the carbonyl carbon, R is still there. You'll make two, not one, but two new carbon-carbon single bonds, very special, very rare, hydroxyl group, plus another alcohol, which comes from here. So here's R prime, here's our triple prime. So let's start here. Carbon, this one right here, have a hydroxyl group. R is methyl. R triple prime is methyl. So I have my two R triple prime, I get that alcohol. And the second alcohol is R prime, and I'll get methanol. And that's how, oh, that was so much. We got to do another one. put it down here. I can still go with a straight arrow. And have fun. What would be the two products that you would get when you do that reaction? Now we're getting some really sophisticated organic chemistry, really sophisticated and fun. All right, everybody's done, so I better get to work. And again, identify the functional groups. Look where what's different. What's not carbon or hydrogen or carbon-carbon single bond. Oh, oxygen, oxygen, same carbon, carbonyl, oxygen. On this carbon, oxygen, we have carbons. I'll call that R prime. On the carbonyl carbon, we have carbons. I'll call that R. First step, ooh, two of something. And what is it? Carbon, magnesium bromide. That's a Grignard. Remember, X can be chlorine, or in this case, bromine, or iodine. Second step, acid and water. Keep your eye on the carbonyl carbon. What's attached to it is still attached to it, becomes an alcohol. Then we make not one, but two carbon-carbon single bonds, very special, very rare in organic chemistry. And this part of the esters, we make a second alcohol. So what's our? Here's my carbon here. That was the carbonyl carbon. I have an alcohol. And what's my R triple prime? Notice the carbon with the magnesium halide is the carbon bonded to this carbon right here. So that's isopropyl group, two of them. If you bond it to the wrong carbon, I'll mark it wrong. We get that. Wow, that's an awesome looking alcohol. And this R prime right here makes the second alcohol, in this case, ethanol. which you can distill off very easily. Think about that. Look at this molecule. That's really complex. I took a simple ester and a simple Grignard, which I can make from isopropyl alcohol, and I was able to make that molecule, this alcohol. The second one, well, I can recycle for other stuff, but this first alcohol, that is complex. And just a quick thing, I'm going to turn the switch totally off. When I see this type of reaction, because I'm a synthetic organic chemist, I think of how can I make that Grignard from an alcohol I could buy? For HBr, or to put a bromine on there. Again, I'm just having fun, excuse me. And react this alkyl halide with a Grignard. And I've done reactions like this to make special Grignards, starting with alcohols. And these are all reactions you learn. And the reason I'm doing this is how an organic chemist works backwards in synthesis. All right, if I'm trying to make this alcohol, how can I make it? This Grignard. If I can't buy this Grignard, how can I make it? From this alcohol, I can get my hands easily on 2-propanol, otherwise known as isopropyl alcohol. I can get HBr, I get magnesium, I can make that. And I could also make the ester if I couldn't buy it. And that's how an organic chemist thinks, or at least a synthetic organic chemist like Dr. White. All right, now, as we move on, I have been sheltering you from something. Oh no, yes, I have. And that is, up to now, I've kept what we've been doing in reactions very basic or simple in terms of there's only in a molecule one functional group. What happens if there's more than one, like 2? Well, if they're the same, they react like they're alone most of the time. For this class, all the time. So let me show you something. Now, there's something called polymers, and I'll teach you later on about polymers. We'll have a whole chapter, really only a whole chapter. We'll only spend about an hour and a half, 2 hours at most. I could do a 2-semester graduate level course, even a 4-semester on polymers. And I have patents in polymers, so I know this stuff. And I'll teach you later on, poly means many, mer units. Think of a polymer as a long freight train, where boxcars are groupings of molecules. Well, polyesters is an important polymer in our life, and poly means many. And what unit or functional group is holding these units together, like the couplers of a boxcar? By the way, Dr. White's a train enthusiast, have been since I was 5. My father used to take me down on the weekends to the train yards on the south side of Chicago. We'd stand outside the fence and watching these big behemoth steam engines come in and being serviced. And they had couplers, and this is called a knuckle coupler. But let's look at the following. This is a diacid, and it's got a common name, terephthalic acid. Right now, the switch is clicked. This won't be on a test, but this is important in our daily life. And I'd like to talk to you about it. How it got that name, terephthalic acid, I have no idea. It's got a benzene ring, but that's not going to react. But notice it has not 1, but 2 carboxylic acids. Next, we have ethylene glycol, and that's a common name that has a molecule with not 1, but 2 alcohols. So let's take a look at this reaction. If I added some acid catalyst, what do we have? Well, I've got a carboxylic acid plus an alcohol. And you learned, or hopefully will learn, that forms an ester. So if I react this with this, I will get this molecule. If you look at this end, I still have a carboxylic acid, and this end, I still have an alcohol. So if I were to react this with more terephthalic acid, and don't copy this down, if I were in a classroom, I'd be telling the class that, and you'd be seeing me fill up the whole whiteboard with what I'm going to do. This is a carboxylic acid. This is an alcohol. You'll make an ester. So this part, think of as the R prime of this alcohol. So I will get my terephthalic acid, this right here. This side does not react at this point. And I get this molecule. And notice at this end and at this end, I have a carboxylic acid. I can react it with more ethylene glycol. I'm not going to redraw the whole thing. I'll just replace this with this, make this new ester. Then here, this can react with more phthalic acid. This can react with more ethylene glycol, and it'll keep on repeating over and over again. And what's the repeating unit? This molecule. And notice I have in a bracket a benzene ring, carbonyl, OCH2, should be subscript O, and N. That repeats over and over and over again. And I can make it where N is about 1 million or even 1.5 million. Huge. Think of a long train that you get stuck for hours. No, I don't want to think about that. But anyways, what do we call this? All right, hold on 1 second. This is called polyethylene terephthalate. Polyethylene terephthalate. Polyethylene terephthalate? Boy, that's a lot to say. Polyethylene terephthalate. Boy, my jaw. Am I getting thirsty? Yes, I am. Polyethylene terephthalate. Oh, that's making me real thirsty. You know something? I'm a lazy organic chemist. I'm going to just shorten that. And what am I going to shorten it to? PET. This is the molecule called polyethylene terephthalate, PET. That's what's making this water bottle. And when you go to any store and you see a plastic bottle with liquid in it, it's this polymer, PET. You know, if you have your favorite pop, you know, like Dr. Pepper or Verner's or 7-Up. I haven't drank 7-Up in a long time. I used to be addicted to it at one time. this plastic in my water bottle. That's polyethylene terephthalate. And asking, why am I learning this organic chemistry? Well, the obvious answer, as you've heard me say many times, for you is you want to get a good grade so you can get into a program or a school. Why learn it? Well, the reaction making an ester is used to make this bottle and other plastic bottles, like the 2-liter bottles for pop and or water or whatever they put in them. All right. Guess what? We're done with this chapter. If you haven't noticed, I'm picking up speed, and that happens in the semester, part of the semester. What that means is next week, well, I gave you off so you don't have to come, but a week from today, no, 2 weeks from today, next week, not 2 weeks from today, a week from this Monday, the Monday when we come back from spring break, I will go through the carboxylic acid and ester problem set and make sure you work on it over break. And guess what else time it is? It's new chapter time, new functional group time. I had to do that a second. This is my favorite. Was company that made these are from West Germany, and that company no longer exists, and you can't get these quality anymore. I've got 4 of them, and they will never leave my house. They're too valuable. But anyways, it's new chapter time, new functional group time. Now I have to warn you, if I look like I'm really having a good time, I am, because this new area I'm a world authority in. I also have 9 US patents in this area, so I think I know a little about it. And what's this new area? And this new area is called, or chapters, which are a combination of, if you're reading the book, chapter 11 and 13, amines, amides, and heterocyclic compounds. And we're going to get in some really amazing stuff. I'll be teaching you this chapter how fabric softener works. I'll also teach you about your skin a little. I'll also teach you about things you bite into that are blazing hot, hot peppers. And I'll also teach you, and this, yeah, I'll teach you now, I'll talk about it later. No, wait until later. How, I might do it now. How to get rid of that burn in your mouth when you've eaten a hot pepper and you're in serious pain. I'll also talk about one of the dumbest things Dr. White's ever done in my life. I've done a few, this was pretty dumb. All right, what's an amine? Well, an amine is an organic derivative, something made from ammonia. Now, ammonia, in case you forgot, is this molecule. And amines are where you replace the hydrogens on ammonia with alkyl groups, are cycloalkyl groups, or aryl groups, which is another way of saying benzene rings. And those are called the amines. Now, interesting thing, we've only dealt with carbon and oxygen, and mainly carbon. And carbon has 4 valence electrons. This won't be on a test, and therefore it forms 4 bonds to get an octet. Now, nitrogen has 5 valence electrons. So to get its octet, it normally has 3 bonds. But unlike carbon, it has this non-bonding pair of electrons. Oh my God, I got so excited. No, actually, I'm on time. I was thinking of the second break. We're on the first break now. And those can be, on special occasion, involved in a bond. And therefore, nitrogen can have 3 bonds to it or 4 bonds to it. Unlike carbon, which is always 4, never more, never less, nitrogen can have 3 or 4. The single electrons can be formed to form a bond, 3 bonds, and the lone pair of electrons that are non-bonding pairs can also bond. So that's interesting about nitrogen. Now, switch is totally off for this slide, but I'll use this terminology in our class, so I better teach you it. It will never be on a test. Now, primary amine is when you have one R group on a nitrogen in an amine. Notice I have 3 bonds to nitrogen. 1 plus 2 here equal 3. Now, secondary amine, remember we're having ammonia and we're replacing some of the hydrogens. A secondary amine is when you replace 2 hydrogens, and they can be the same or different R and R prime. And a tertiary amine is when you replace all 3 hydrogens. Now, each of these, and I really rarely show them, have non-bonding electrons. You don't have to show them. And primary 1R group on nitrogen, secondary 2, tertiary 3. Notice each one of these has 3 bonds to nitrogen. Now, it turns out these non-bonding electrons can also bond, and you're going to have to wait until after the break to find out, because I'm going to give you a cliffhanger. And with that, time for a 5-minute break. I'll see you in 5 minutes. I'm going to get up and stretch.
Dr. White, we can't hear you.
Thank you for letting me know. Can you hear me now? Test, test, number
Yeah.
9, number 9. That comes from Woodstock. Do people know what Woodstock is? I think I just did a generation. Oh, one of you do. All right, let's talk about quaternary ammonium salts. Now, quaternary ammonium salts have this structure. And because you use the lone pair of electrons here in this bond, this nitrogen now has a plus charge, and all molecules in nature have a net zero charge. So we also need an anion. And there are many anions, but for this class, I'll keep it to the halogens where X equals, for this class, chlorine, bromine, or iodine. And this is a quaternary ammonium salt. Now, important to know, this halogen is not bonded to that R group. It's actually bonded to the nitrogen by an ionic bond, which we haven't really talked about much in this class, but that's an ionic bond. Each of the R groups are covalently bonded, sharing pairs of electrons to the nitrogen. And this is called a quaternary ammonium salt. And I'm going to try and be a good boy. I don't know about a boy. I think that, no, anyways, I'm going to try and be a good organic chemist, and I won't use slang because that's not proper. But if you work in industry and in quaternary ammonium salts, which I'm a world expert in, we call them not quaternary ammonium salts. We just call them quats for short. Organic chemists are lazy, but I won't do that in this class. I'll try and stay very professional. Now, I will tell you, and I'll talk more about it, 2 key uses of quaternary ammonium salts are antimicrobial compounds are quaternary ammonium salts, or it's a major area quaternary ammonium salts are used. And the other is as a fabric softener. If you use a fabric softener, which I do, and I have a couple molecules I invented that are used as fabric softeners, those are all quaternary ammonium salts. And when I worked at Nobel, now it's called, actually that division is sold off, it's called Nourion. When I was there, it was Axochemy. I was in charge of nitrogen derivatives, including quaternary ammonium salt for all of North America. Oh, my ego trip, I'm just starting, woo. But anyways, and I worked heavily with companies that we sold to, like Procter & Gamble and Lever Brothers. And later on, not today, I'll tell you a great story about P&G, Procter & Gamble, and something I had to do with them. And I'll also tell you a story about Lever Brothers. And how many of you have ever seen the Snuggle teddy bear? I'll tell you the true story about that, which I learned when I was in a pub with some people getting drunk in London. Actually, we were not in London, we were in Littleborough. All right, so primary amine, 1 R group on nitrogen, secondary amine, 2 R groups, tertiary, 3 R groups, quaternary ammonium salt, 4 R groups, but it has a positive charge on nitrogen, and you need an anion. And for this class, we'll use the halogen anions. Now, in real life, which I've worked in, still do, we don't use IUPAC for nomenclature for amines and quaternary ammonium salts. We use common names. Now, how do you do common names? You name the alkyl group, list the alkyl groups, or better yet, I should change this. for primary, secondary, and tertiary amines, name the R groups as alkyl groups in the front of the name, and then 2, at the end, add the word amine. It's pretty simple. Similar to alcohols, except you don't use alcohol, you use the word amine. So let's take a look at this. And let's put a molecule on the board. And now, once again, look for what's different, what's not carbon, what's not hydrogen. Ooh, nitrogen with carbons on it, hydrogen. This is a primary amine, which I won't ask you, but it's an amine. How do you name it? What's my R group here? N-propyl. And it's an amine. So there you go. Now, I have to show you something important that we never did with carbons to any extent, but we do a lot in organic chemistry with nitrogen. And that's this molecule. This would be an amine, nitrogen with carbons, secondary amine, which I'll never ask, and then we'd call this dimethyl, di is 2, amine. But you can write it this way, or, which most organic chemists do, we'll write it this way. And this is something you should know and understand. And this is also dimethylamine, 2 R groups on a nitrogen. When they're the same, we can pop them in a bracket. And if I had this molecule, remember there are 3 bonds to nitrogen in amines. This would be tri, because there are 3, and propyl amine. And this one you might want to say, Dr. White, how come there's no nitrogen? Well, in amines, you only have 3 bonds to nitrogen, and we've got them. Now, you could also write it this way. On a test, I'd accept it. On a test, I'm going to write it this way. But as an answer, if you had to write it, and you can say this, see, this is a lot longer to do. And that's why this is the preferred way. It's quicker, it's easier, and organic chemists are lazy. All right, your turn. Let's have you try a couple. What would be the common name for this molecule? 3 points each. On test 3, I'm going to be changing the nomenclature, which will say give the IUPAC or the common name, because I'm not going to ask you to learn how to do common names of amines. Nobody uses them except for patents and legal documents, which your test is not either. And what I mean by legal documents, contracts. Even then, contracts have been written with common names I've seen. And since there are only 3 of us left, when you're done, give me a thumbs up. All right, let me get going. Look for what's different, what's not carbon, what's not, ooh, a nitrogen. And this is an amine. There's this R group on there, that's ethyl. and you add the word amine. And why don't you try this one? What would be the name of the common name of that molecule? Again, since everybody else is playing hooky, actually not, because I have a lot of people just not come here and watch the videotape. Shh, don't tell anybody, I'm being nice. And that allows some people who'd be working now and not be able to take my class, give me a thumbs up when you're done. Remember, name each R group as an alpha group and then the word amine. All right, so if we look for what's different, we have a nitrogen, and on there we have, this is N-butyl, this is methyl, and it's an amine. Oh, let's do one more. And here's one for you to do. And I'm going to get going. And we'll look for what's different. We have a nitrogen, and we've got, not one, but two ethyl groups. So 2 is diethyl amine. In graduate school, I used diisopropylamine a lot in my research. All right, now on to test number 3, like test number 2, there'll be 2 types of nomenclature question. One is, here's the name, here's the structure, give the name, which for amines can be a common or a UPAC, common would be better. And here's the name, draw the structure. For amines, I'll give you the common name. And if I were to do this, I'm going to start from the right, move left. An amine, I see trimethyl. So I have trimethyl. And remember, we put things in brackets when they're the same. And I'm done. Now you could have, that looks awful. Hold on. That's better. And you could have also written it this way. I won't on a test. So you should be familiar with this way of drawing it. But both of these would be correct. And that's how you do it. So I'm going to give you a couple to try. And why don't you draw this ethyl methylamine? And thank you. All right, so you start from here. Amine, nitrogen compound. What's on there? Methyl and an ethyl. And it doesn't matter which side you put the methyl or ethyl. I'm doing it this way. You could have reversed them. Now, amines have 3 bonds to it. I already have 2, so I need another hydrogen. And why don't you try another one? Dimethyl isopropylamine. Draw the structure for that. Remember, when you're done, give me a thumbs up. All right. How do we do this? We start from here. And amine, what's on there? Isopropyl, dimethyl would be 2 methyl groups and 1 isopropyl. Now for 2, I'm going to do this. Then isopropyl. Now notice this is an amine. I have 2 plus 1, 3. So that's why there are no hydrogens on there. You could have also drawn it this way. And I could have put this over here, this on this side. There are other ways of drawing it. On test, this is the way I'll draw it. My software will. But for your answers, you can put that also. All right, let me explain why we normally use organic chemists to work in this common and not IUPAC. Now, the switch is off. Click, click, double off. How do you name amines with a IUPAC? Well, it's similar to alcohols. And the suffix, which is the part at the end, you find the longest chain, name it as an alkane, but instead of using an OL ending, use the ending A, drop the E, add AMINE. Now, unlike carbons, you can have secondary and tertiary amines. So how do we designate the alkyl group, other ones on nitrogen? By using a capital N. And this is for the substituents on the nitrogen. And let me show you an example of the two. Oh, by the way, you can put a hydrogen there, or you can put it underneath. I do both. I'll talk. All right, did we boop out already? Hold on. All right, I've got to do something. I probably, hopefully soon, well, maybe I don't know when, I should really get more memory, even though I should have enough for this machine. All right, we're back in business. Sorry about that. All right, so the question is, how do we name this amine? All right, then let me let you see it. All right, thumbs up. Everybody see that amine on the whiteboard? Thank you. All right, so first of all, you find the longest chain on nitrogen. That's 4 carbons right here. You name that as an alkane. Drop the E, add amine. Now, which carbon is the nitrogen on? You give it the lowest number, it's on carbon 1. Now, we have a methyl group, and that's not on the chain, it's on the nitrogen. And to show it's on the nitrogen, I'll call it capital N methyl 1-butanamine. Now, common name would be and that's why common names are preferred. And I'll never ask on a test or a final IUPAC will be using common, because in real life, most people work in this area, like all of them, use common names, not IUPAC. You see an organic chemist using only IUPAC, he's never worked in industry, or she, not to be sexist. All right, what I don't have here, oh, by the way, when you have amines present with other functional groups, the amine group, and I'll teach you this later when we get into proteins, the amine group is called an amino group and is treated as a substituent, just like a chlorine, bromine, or iodine is a substituent. All right, now what I don't have here is how to name quaternary ammonium salts. Bad, Dr. White. And here again, common. And just like amines, you name each R group as an alkyl group in front. Now, something different at the end, you name the phrase ammonium. I can spell it right. Ammonium halide. And for this class, what I mean by halide is chlorine minus is chloride, bromine minus is bromide, and iodine minus the anion is iodide. Again, this is the halide in X in quaternary ammonium salts. So let's take a look at a couple of these. And if we look at this molecule, look for what's nitrogen, what's not carbon, and it's got 3 + 1, 4 groups, and it's got an anion too. This is a quaternary ammonium salt. So I have ethyl, and it doesn't matter which order you put this in because it's common names. Trimethyl, and then it's a quaternary ammonium salt, ammonium. My eyes want to become a U. Stop doing that, Dr. White. Ammonium chloride. Again, name the alkyl groups. Add the word ammonium. Then for chlorine, it's chloride, bromine, Br minus, bromide, I minus, iodide. Now, 4 is tetra, but let me do this one for you, or better yet, let you do this one. And what would be the common name of that molecule? Give me a thumbs up when you're done. All right, let me get going. Look for what's a nitrogen with 2, 4 positive charge and an anion. This is a quaternary ammonium salt. We have dimethyl, or you could have said diethyl, order's not important. Dimethyl, di meaning 2. Oops, wrote the same thing. I need a week off. You can take the next week off too. Diethyl, and then ammonium. And then up here, minus is iodide. Now, there's a very special quaternary ammonium salt that's very near and dear to my heart, and that's this one. And this one you should know the name of. Now, R sub T, and I'll talk more about the exact structure when we get into fats and oils, is an alkyl group with 16 to 18 carbons with and without a double bond. It's called tallow. This T stands for tallow. And I'll explain when we get in fats and oils where that comes from. But this would be called ditallow, dimethyl, ammonium, because it's a quaternary ammonium salt, and Cl minus is chloride. And until about maybe 10 to 15 years ago, this was the only molecule used as a fabric softener. I think I spelled that wrong. Hold on while I use my favorite spell check. Google. I did spell it right the second time. I don't know if I told you this, but I was always the first one down in the spelling bee. And ditallow dimethyl ammonium chloride for until about 10, 15 years ago was the only molecule that was used as a fabric softener, like in Downy or Snuggle, two main brands in the United States. And I worked for a company that for many, many years was one of the two main producers of that molecule in the United States and the world even. And that molecule helped me get me around the world, to Mexico, to Europe, to Canada. It also helped pay for a couple of cars and a whole lot of other stuff. So it's very near and dear to my heart. And you should know this is ditallow dimethyl ammonium chloride. Now, some practical stuff. Since I know fabric softeners, I worked in that industry. I also worked with companies that made them, Procter and Gamble, and also Unilever, Lever Brothers. Back then it was called part of Unilever, Snuggle and Downy. One of the things I learned from those people who are experts, they sold it, was you know how you can have two different types of fabric softener, liquid or the sheets. The sheets work better. And I've been using it for a long time, and I've learned that. Yes, if you pour it in as a rinse cycle, it will work, but the sheets work much better in your dryer. Now, the other thing I like to teach you is if you've ever had towels or dish towels in the kitchen and they don't absorb water that well anymore. Are they old and broken? No. What R is, R sub T in a quaternary ammonium salt is a long chain that makes your clothes feel smooth. But at the same time, it stops it from absorbing water. When we get into fats or carbohydrates, I'll teach you the actual chemistry, how towels work. But for now, I just want to give you a little heads up. So if your towels aren't working as well as they used to, what you do is next time you wash them and then dry them, don't use a fabric softener. Do that about once or twice. What you're doing is stripping off the excess fabric softener to allow your towels to absorb water better. Aren't you glad you took my class? I know all these deep things about the real world. Now, if I look at the clock, in real life, if we'd been face to face, I'd only go 50 minutes, then we go for a lap. So what I'm going to do in honor of spring break coming up next week, it's lab time. All right, we'll come back to quaternary ammonium salts and amines, I guess, a week from this Monday. So let's look at today's lab. Oh, I got to open today's lab. Hang in there. I got to open one more thing. Bingo. Got it. All right, everybody see aldehydes and ketones on your screen? Thumbs up, people. Thank you. All right, today's lab deals with aldehydes and ketones. And remember, an aldehyde, carbonyl with a hydrogen R group, aldehyde. And a ketone is a carbonyl carbon double bond to oxygen with two R groups on here. This is a ketone. And in keeping with the labs we've been doing all semester, and if we were face to face, I'd be telling you this. I have people look at you, the students, investigate some common properties of aldehydes and ketones for this lab. Now, the first one is water solubility. Are they soluble in water? And what are structural features that help make things soluble or insoluble? And what you would be doing if we were face to face, you take some test tubes, you fill them about halfway with water, then you'd put a couple of drops of each aldehyde or ketone into there, you'd mix it. If it was the same throughout, homogeneous, it's soluble. If it's separate layers, it's insoluble. Now, here are the ones you would be testing. And since we're not going to do this at home, I gave you the data. Now, notice here in red, it says, draw the structures for the compound for the table before. So like for cyclopentanone, underneath, you should draw it there. Heptaldehyde. By the way, I used the common name, ouch. This should be that's actually heptanal. Sorry about that. Wow. I know my common name so well, I forgot I even had it there. And that's first part. Now, the second part, I'd have you smell this, but we're going to omit this because I don't want you to be influenced by my nose. Now, next one is oxidation of aldehydes and ketones. Let's take a look at this on the whiteboard. And here, if you have an aldehyde and you oxidize it, and we're going to be using potassium permanganate. This is purple. And this is usually clear or slightly yellow, very faint yellow. And if you can oxidize aldehydes. And what you get is a carboxylic acid. Now, when this is oxidized, this gets reduced and you get manganese dioxide. This is a muddy brown. Now, where this is a test to distinguish between aldehydes and ketones, did I use potassium permanganate or did I use sodium dichromate? Hold on one second. Yep, I used potassium dichromate. Sorry about that. Just wanted to check I was doing the right thing. And if you take an oxidizing reagent with a ketone, you will get no reaction. And it stays purple. So this is a way of telling the difference. Do I have a ketone or aldehyde? Before, organic chemists had the electronic instrumentation we now have. One of them would be infrared spectroscopy. The other one is nuclear magnetic resonance spectroscopy. We would use this test and it would tell you, is that an aldehyde or ketone? Sometimes that's a very important concept to know. And here in a dry test tube, you put about 1 or 2 milliliters of the reagent. This is in a liquid form, dissolved in water. I think it's a little acid to make it go quicker. And then you'd add about 5 drops of the ketone or aldehyde being tested, mix it, wait about a minute, and observe. Now, since we're not doing this at home, but that'll be dangerous, if you have benzaldehyde, you get a muddy brown. If you have cyclopentanone, you get purple. And to make it exciting, there's an unknown compound. And the district attorney of Kane County wants to know, is unknown one a ketone or aldehyde? Because that way we can convict the district attorney, a criminal or a potential criminal, of a heinous crime. I'll let you fill in the blank, what is a heinous crime? And when we mix that with potassium permanganate, it's muddy brown. Now, on this table, you don't have to show the structures. Now, finally, the last reaction we're going to do, and I wish we were face-to-face, but we're not, is called a cross-aldol condensation. And this one, we're going to take benzaldehyde, react 2 of those with acetone in the presence of sodium hydroxide, and I didn't put it here, for a solvent, we'll use ethanol. You can use water, but ethanol does this better. And you get this huge molecule that's called dibenzyl acetone. That's the common name, not the IUPAC name, which I could do, but I'm not going to for you. And this is a fun reaction. I would ask you to watch this YouTube. By the way, here's a YouTube I would ask you to also watch for part 3. Now, in this reaction, if we were face-to-face, you'd add 1.3 milliliters of benzaldehyde, 0.5 milliliter acetone, 7.5 milliliters of ethanol, in that sequence in an Erlenmeyer flask. You know, it looks like a triangle almost, but it's not. It's an Erlenmeyer flask. You'd swirl it, then you'd add 2.5 milliliters, 2.5 milliliters of a 5% sodium hydroxide solution, and you swirl that for 5 minutes. Now, afterward, you put it in an ice bath, let it cool, because that makes the solid, which is this compound. These are liquids, and it precipitates out, becomes a solid. And we can separate it by what's called vacuum filtration using a Buchner funnel and filter paper. And you let it dry on there. And if we were in ECC, since I don't have the time, well, I think this one we do the melting point. Students get this melting point for the dibenzyl acetone. It's a degree or 2 lower than the literature value. Now, let me do one thing. Does everybody see that on the right, the picture? All right, this on top is called a Buchner funnel. And over here on the far left, you can see a ceramic one. I have actually a collection of these. And you put filter paper, and I'll show you a better picture of a Buchner funnel in a second. Well, here's one right here. And you see it's got little holes in the side there. On top of that, you put filter paper. And then what you do, there's a Erlenmeyer. Here's a picture of it. It's called a sidearm Erlenmeyer. And you have we use a better thing than a rubber bong. It's a cone, and it does the same thing. Then here we have an Erlenmeyer with a glass sidearm. and you have a rubber tubing. Here you have a hand pump. We have house vacuum, and it hooks up to the vacuum. The vacuum pulls liquid down through here, but keeps solid the product you make on the filter paper. And this is a way organic chemists use to separate solids from liquids in the lab. You could use a centrifuge. Not really, this doesn't work as good. This works good. And that's how you would separate it. Now it's time for Dr. White to have some fun, and also you should pay attention. All right, thumbs up, people. Do you see what's called the mechanism? All the steps on your screen right now? Thank you, Vivian. All right, let's look at this right here. Over here, I have my 2-benzaldehyde and my acetone. Now, you learned for test 2 that if you have a ketone or aldehyde, the alpha carbon, the carbon attached to the carbonyl, has acidic hydrogens, which you can pull off with a base to make an enolate anion. Now, if we look at benzaldehyde, here's the carbonyl carbon, and the carbon on the benzene ring has no hydrogens. And this is why it's an important thing of what we call a cross-aldol condensation. So the first step, and this is the key step of this reaction, and this is the key step of this reaction, is the base reacts with acetone to form this enolate anion. This enolate anion will attack the carbonyl carbon of benzaldehyde to form this molecule. Now, something I haven't taught you, and it'll never be on test in class, is that when you can have conjugation, alternating single, double bonds, it makes a molecule more stable. And molecules, if they can lose something stable to become more stable, they do. And if you look on this carbon, I have an alcohol. I have a hydrogen there, HOH, H2O. If I lose water between these two carbons, I'll form a double bond. Now we have in the ring double bond, then single bond, double bond, single bond to the carbonyl. And that happens instantaneously, fast. Now, this new molecule right here, on this side, we have alpha carbon with hydrogens, and base will make this enolate anion. And this enolate anion will react with this benzaldehyde, the second benzaldehyde, to form this aldol product, this alcohol right here. And once again, if I can form a double bond that helps give me conjugation, I'll make it stable, more stable molecule. And here I have a double bond, the benzene ring, double bond, the carbonyl. If these two carbons here on the right, if I lose a hydrogen there and a hydroxyl group there, I lose water. Between those two carbons, I form a double bond, and guess what? I've made my product. So the key reaction here is making the first step, the enolate anion. And I have questions for you to answer. Now, important thing to remember, next week, we're not going to have any class. It's spring break. Therefore, I can't ask you to hand in a lab next week. So today's lab is due 2 weeks from today, not 1 week, 2 weeks. And with that, I'm done. Yeah, I'll let you out a lot early, which we normally would have done. I've caught up for the rest of this week and next week. By the way, if you're undergoing Dr. White withdrawal symptoms, always feel free to come to the YouTube channel for Chem 170 and you can see me. With that, I'm done. And I'm going to say, gang gesund, goodbye. Have a wonderful spring break. Gang gesund. I'll see you a week from this Monday. Bye. And if you're going anywhere nice, send me a postcard or an email. Having a great time. Glad you're not here. With that, gang gesund. Goodbye. I'll see you a week from this Monday. Bye now.